The difference in load calculation approaches arises from the type of load and the electrical system configuration. Let's consider 2 and 3 pole circuits with evenly distributed loads. For loads that draw power equally across both phases of a 2-pole circuit, the load current, and thus power, is divided evenly between the phases. For loads that draw power equally across all 3 phases of a 3-pole circuit, the load current, and thus power, is distributed equally among the phases. In such cases, it is appropriate to calculate the load kVA for each phase individually, as the load is balanced across the phases. Next, let's think about 2 and 3 pole circuits with unbalanced loads. Loads that do not draw power equally across all phases create an imbalance in the system. In such cases, it is necessary to calculate the load kVA for each phase separately, taking into account the uneven distribution of load. Both approaches are correct depending on the load type and system configuration. For balanced loads, calculating the load kVA for each phase individually is appropriate. For unbalanced loads, calculating the load kVA for each phase separately is necessary. The approach taken will affect the calculated service size. If the load calculation assumes that the load is evenly distributed across the phases, the calculated service size will be smaller. If the load calculation takes into account the unbalanced load, the calculated service size will be larger to accommodate the high demand on certain phases. Consider an example. If a 2.3 kilowatt load is evenly distributed across both phases of a 2-pole circuit, it is appropriate to calculate the load kVA for each phase as 1.15 kilowatts, which is 2.3 kilowatts divided by 2. However, if the load is unbalanced, such as with a single-phase motor, it would be necessary to calculate the load kVA for each phase individually. When dealing with electrical load calculations, understanding the concepts of balanced and unbalanced loads is crucial for accurate system design and safety. A balanced load refers to a scenario where the power drawn by a load is distributed equally across all phases of a multi-phase electrical system. This is commonly seen in 3-phase systems, where the load on each of the 3 phases is approximately the same. On the other hand, an unbalanced load occurs when the power drawn by the load is not evenly distributed across the phases, resulting in different current levels in each phase. Understanding whether a load is balanced or unbalanced is essential for several reasons. Firstly, it affects the sizing of electrical components such as conductors, transformers, and protective devices. Balanced loads allow for efficient utilization of these components, as the current is evenly distributed, minimizing losses and voltage drops. However, unbalanced loads can lead to high current levels in certain phases, requiring larger conductors and potentially dirting of transformers to prevent overheating and damage. Secondly, balanced and unbalanced loads impact the performance and stability of the electrical system. Imbalanced loads can cause voltage imbalances, which can negatively affect sensitive equipment and lead to increased energy consumption. Moreover, unbalanced currents can create circulating currents in the neutral conductor, increasing losses and potentially overloading the neutral, posing a safety hazard. To determine whether a load is balanced or unbalanced, several factors need to be considered. These include the type of load, the connection configuration, and the load distribution. Resistive loads, such as heaters and incandescent lights, typically draw current equally across all phases, resulting in a balanced load. However, inductive loads, such as motors and transformers, can create unbalanced loads due to differences in impedance and winding configurations. The connection configuration also plays a role in determining load balance. Delta-connected loads are inherently more susceptible to imbalance compared to Y-connected loads, as any imbalance in the load is directly reflected in the line currents. Similarly, single-phase loads connected to a 3-phase system can create significant imbalance if they are not evenly distributed across the phases. Load distribution is another critical factor to consider. Ideally, loads should be evenly distributed across all phases to minimize imbalance. However, in many practical scenarios, this is not always possible, especially in commercial and residential buildings where single-phase loads are common. In such cases, careful planning and load management are necessary to mitigate the effects of unbalance. Several methods can be used to address unbalanced loads and improve system performance. Firstly, load balancing techniques can be employed to redistribute loads across the phases as evenly as possible. This can be achieved by strategically assigning single-phase loads to different phases or by using load balancing transformers. Secondly, phase correction equipment, such as capacitors and reactors, can be used to compensate for reactive power imbalances and improve power factor. Thirdly, active harmonic filters can be installed to mitigate harmonic currents caused by nonlinear loads, which can exacerbate voltage imbalances. Finally, proper grounding and bonding practices are essential to minimize neutral current and ensure safety. In summary, understanding the concepts of balanced and unbalanced loads is crucial for electrical system design and operation. By considering the type of load, connection configuration, and load distribution, engineers can assess the degree of unbalance and implement appropriate measures to mitigate its effects. Load balancing techniques, phase correction equipment, active harmonic filters, and proper grounding practices can all contribute to improving system performance, reducing losses, and ensuring safety. In practical applications, it is important to consider the specific characteristics of the electrical system and the loads connected to it when determining the appropriate load calculation approach. For instance, in industrial facilities with large motor loads, it is crucial to accurately assess the starting currents and running currents of the motors to ensure that the electrical system can handle the demand. Similarly, in commercial buildings with a mix of lighting, HVAC, and electronic equipment, it is necessary to consider the diversity factors and demand factors of these loads to avoid oversizing the electrical system. In residential buildings, the load calculation is typically based on the square footage of the building and the number of appliances and lighting fixtures. However, it is also important to consider the potential for future load growth, especially with the increasing adoption of electric vehicles and other energy-intensive devices. Furthermore, it is essential to comply with the applicable electrical codes and standards when performing load calculations. These codes and standards provide guidelines and requirements for sizing electrical components, protecting against overcurrents and short circuits, and ensuring the safety of electrical systems. In the United States, the National Electrical Code, or NEC, is the primary standard for electrical installations. The NEC provides detailed requirements for load calculations, conductor sizing, overcurrent protection, and grounding. It is important to consult the latest edition of the NEC and any local amendments to ensure compliance with the applicable regulations. When performing load calculations, it is also important to consider the voltage drop in the electrical system. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can negatively affect the performance of electrical equipment and cause them to operate inefficiently. To minimize voltage drop, it is necessary to select conductors with adequate ampacity and to keep the conductor lengths as short as possible. The NEC provides guidelines for calculating voltage drop and recommends limiting the voltage drop to a maximum of 3% for branch circuits and 5% for feeders. In addition to voltage drop, it is also important to consider the effects of harmonics on the electrical system. Harmonics are sinusoidal voltages and currents that are integer multiples of the fundamental frequency, typically 60 Hz in the United States. Harmonic currents are generated by nonlinear loads such as electronic equipment, adjustable speed drives, and arc furnaces. Harmonic currents can cause a variety of problems in electrical systems, including increased losses, overheating of transformers and conductors, and interference with sensitive electronic equipment. To mitigate the effects of harmonics, it is necessary to use harmonic filters or to specify equipment that generates low levels of harmonics. The Institute of Electrical and Electronics Engineers, or IEE, provides standards for harmonic control in electrical power systems. In summary, load calculations are a critical aspect of electrical system design and should be performed carefully and accurately. By considering the type of load, the connection configuration, the load distribution, the voltage drop, and the effects of harmonics, engineers can ensure that the electrical system is properly sized, protected, and operates efficiently. Compliance with the applicable electrical codes and standards is essential for ensuring the safety of electrical systems. Let's discuss diversity factors and demand factors. These are crucial considerations in electrical load calculations, especially in determining the appropriate size of electrical services and distribution equipment. Diversity factor is the ratio of the sum of the individual maximum demands of the various loads in a system to the maximum demand of the entire system. It is a measure of how likely it is that all the loads will be operating at their maximum demand simultaneously. The diversity factor is always greater than or equal to 1. A diversity factor of 1 indicates that all the loads are expected to operate at their maximum demand simultaneously, while a diversity factor greater than 1 indicates that the loads are not expected to operate at their maximum demand simultaneously. Demand factor, on the other hand, is the ratio of the maximum demand of a load to its total connected load. It is a measure of how much of the total connected load is actually used at any given time. The demand factor is always less than or equal to 1. A demand factor of 1 indicates that the load is always operating at its total connected load, while a demand factor less than 1 indicates that the load is not always operating at its total connected load. Both diversity factor and demand factor are used to reduce the calculated load for electrical services and distribution equipment. This is because it is unlikely that all the loads in a system will be operating at their maximum demand simultaneously. By applying diversity factors and demand factors, engineers can avoid oversizing electrical equipment and reduce costs. The appropriate diversity factors and demand factors to use depend on the type of loads in the system, the occupancy of the building, and the operating characteristics of the loads. Electrical codes and standards, such as the NEC, provide guidance on the appropriate diversity factors and demand factors to use for different types of loads. For example, the NEC provides demand factors for dwelling units, commercial buildings, and industrial facilities. These demand factors are based on historical data and engineering judgment and are intended to provide a reasonable estimate of the maximum demand of the loads in the system. In addition to the demand factors provided in the NEC, engineers may also use their own judgment and experience to determine the appropriate diversity factors and demand factors to use for specific projects. For example, an engineer may consider the operating schedules of the loads, the likelihood of simultaneous operation, and the impact of load management strategies when determining the appropriate diversity factors and demand factors. It is important to note that the use of diversity factors and demand factors can significantly reduce the calculated load for electrical services and distribution equipment. Therefore, it is essential to use these factors carefully and to ensure that they are appropriate for the specific application. Overly optimistic diversity factors and demand factors can result in undersized electrical equipment, which can lead to overloading, voltage drop, and equipment failure. In summary, diversity factors and demand factors are important considerations in electrical load calculations. These factors are used to reduce the calculated load for electrical services and distribution equipment, taking into account the likelihood that all the loads in a system will not be operating at their maximum demand simultaneously. The appropriate diversity factors and demand factors to use depend on the type of loads in the system, the occupancy of the building, and the operating characteristics of the loads. Engineers should use these factors carefully and ensure that they are appropriate for the specific application. Now consider the application of load calculations for mechanical panels. Calculating the service size for mechanical panels involves understanding the specific loads they serve and applying appropriate factors to account for their operational characteristics. Mechanical panels typically supply power to equipment such as HVAC systems, pumps, fans, and other machinery essential for building operations. The process begins with identifying all the loads connected to the mechanical panel. This includes determining the horsepower or kilowatt rating of each motor, the voltage and phase requirements, and any specific operational characteristics such as whether the motor is continuous duty or intermittent duty. Once the loads are identified, the next step is to determine the demand factor for each load. Demand factor, as previously discussed, is the ratio of the maximum demand of a load to its total connected load. For mechanical equipment, The demand factor may vary depending on the type of equipment and its operating schedule. For example, a continuously operating pump may have a demand factor close to 1.0, while an intermittently operating fan may have a lower demand factor. The NEC provides guidance on the appropriate demand factors to use for different types of mechanical equipment. These demand factors are based on historical data and engineering judgment and are intended to provide a reasonable estimate of the maximum demand of the loads. After determining the demand factor for each load, the next step is to calculate the total demand load for the mechanical panel. This is done by multiplying the connected load of each piece of equipment by its demand factor and then summing the results. The resulting total demand load represents the maximum amount of power that the mechanical panel is expected to draw at any given time. In addition to the demand load, it is also important to consider the starting current of motors connected to the mechanical panel. Motors draw significantly higher current when they start than when they are running. This starting current, also known as inertia current, can be several times the motor's full load current. The mechanical panel must be sized to accommodate the starting current of the largest motor connected to it. The NEC provides guidelines on how to calculate the starting current of motors and how to size the conductors and overcurrent protection devices to accommodate this current. After calculating the total demand load and the starting current of the motors, the next step is to size the conductors and overcurrent protection devices for the mechanical panel. The conductors must be sized to carry the total demand load continuously without overheating. The overcurrent protection devices, such as circuit breakers or fuses, must be sized to protect the conductors from overloads and short circuits. The NEC provides detailed requirements for sizing conductors and overcurrent protection devices based on the ampacity of the conductors and the interrupting rating of the overcurrent protection devices. In addition to sizing the conductors and overcurrent protection devices, it is also important to consider the voltage drop in the conductors feeding the mechanical panel. Voltage drop, as previously discussed, occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can negatively affect the performance of the mechanical equipment and cause them to operate inefficiently. To minimize voltage drop, it is necessary to select conductors with adequate ampacity and to keep the conductor lengths as short as possible. The NEC provides guidelines for calculating voltage drop and recommends limiting the voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Finally, it is important to consider any future load growth when sizing the mechanical panel. Mechanical panels are often designed to accommodate future expansion or the addition of new equipment. Therefore, it is prudent to add some extra capacity to the mechanical panel to allow for future load growth. A common practice is to add 25% to the total demand load to account for future expansion. In summary, calculating the service size for mechanical panels involves understanding the specific loads they serve, applying appropriate demand factors, considering the starting current of motors, sizing the conductors and overcurrent protection devices, minimizing voltage drop, and accounting for future load growth. Compliance with the NEC and other applicable codes and standards is essential for ensuring the safety and reliability of the mechanical panel.